We're going to go ahead and design a form to support an 8-inch thick floor slabs. And as you can see from the problem, let me just review the problem for a second quickly. And we're going to use the material that we have. It's going to be a Douglas Fir large framing member, and we're going to use steel shoring with the steel support underneath the stringer, and then the stringer are supported by the joists right here, and then we have the plywood on top, and then we have the concrete on top of it. The design we're going to do, it says the bay is going to be 15 feet by 15 feet and 8 feet tall. And also it says that the deflection limit is going to be L over 360 or 1/16, which one control. And we're going to go ahead and use the code and design this. All right, so let's get to work. So what we have is, this is the whole idea. We have a stringer, we have the plywood sheeting. Okay, so this right here is going to be the plywood sheeting. First thing we're going to do, I'm going to say step 1, load calculation. The concrete given to us as 150 pound per cubic feet concrete. So the unit where the concrete is 150 pound per cubic feet. And I have an 8-inch thick slab, so this thickness right here, it's going to be right here. That's going to be, for the concrete, it's going to be 8 inches. All right, so that load, we're going to calculate that load. That's going to be, that load is going to be 8-inch divided by 12 multiplied by 150 pound per cubic feet concrete, and that will give us 100 pound per square foot. And per the code, we're going to go ahead and say, okay, minimum construction live load, it's going to be 50 pound per square foot. And we're going to say weight of the form estimated at 8 pound per square foot. So now my total vertical design load, it's going to be 158 pound per square foot. One thing you got to remember here is this design load is used for bending and fluxual, but for deflection we're going to take the life load out. So we're going to say total load for deflection is 108 pound per square foot. So I'm just going to come up here. Now on step 2, I'm going to go ahead and do a sheeting design. Remember, this is our concrete is going to be right here. And below the concrete, we're going to have this as plywood. It's going to be resting on top of the joist. So we're going to design this sheeting, make sure we have a proper sheeting. And we're going to assume right here 3/4 inch plywood, my favorite. Assuming 3/4 inch plywood, structural grade number 1, which I'm going to have on a board right there. And then we're going to determine its max allowable span. From table, from ACI formwork, table 4.14 or APS also, we're going to go ahead and find this quality. F prime B, the bending capacity already been adjusted. It's going to be about 1545 psi. And the rolling shear is going to be 82 psi. E prime, it's going to be 1,500,000 psi. Also from table 413, which is on the board, that's an ACI table, or you can also go to a PS table in Wood Design. Both of them can you pick up online on Google. And the suction module given, which they call the KS, but that's basically S. And the suction module is given as 0.464, and the moment inertia is given as 0.202. This is the inch by power 4. This should be inch by power 3. And the rolling shear for IB over Q is given as 6.118 inch square. And now we have all these design criteria. We have all these. We're going to go ahead and calculate the check for bending. So we're going to go ahead and check for bending. What we're going to do, because this is a 4x8 sheet, plywood comes in a 4x8 sheet, and we're going to just take a 1 foot strip of it, and we're going to go ahead and use that. So for 1 foot strip, we're going to say, we're going to calculate the load. Load was 158 pound per square foot, and then we're going to use 1 foot strip be our turbotree width, so that will give us a 158 pound per foot. And if we convert that to an inch, divide that by 12, that'd be same as 158. No, I lied. That'd be same as 13.16 pound per inch. Okay, so take a look at what I have on the board. Normally in a class we talk about simply supported span, which is one span. Then we have multiple span, 2 span, 3 span. This is going to be multiple span, so because it's an 8 foot plywood, most likely it's going to be 3 span supported. So based on what I have on the board, we're going to say for a 3 span support. Now remember, what you see on a board you can also see in any steel design, timber design, or ACI book design. All it's a structural analysis, and deflection and load calculation, everything is given in that table. That's to be equal 3.16 square root of F prime B times S divided by W. That's B is a small b actually. Let me correct that. It's a stress, basically bending stress there. So that's the section modules, and that's how we calculate the allowable length. For L is going to come out to 3.16 square root of F prime B came out to be, where are you? 1545. And S came out to be 0.464 divided by the weight, and the weight we're going to use 13.16, and that's going to come out to 23.3 inches. So this is basically telling us that the maximum span length based on bending, it's going to be 23.3 inches. Okay, but there's more than bending. Let's go ahead and check for deflection, see what the deflection does. Let me erase right here. 3 span deflection is equal, delta max is equal, and that is equal WL by power 4 divided by 145 E prime I. So if I go ahead, set delta max is equal L over 360 and set it to that equation, what I'm going to end up with is L is equal, basically I'm going to calculate for the allowable L, and that's a 0.738 time E prime I divided by W, and that's by power 1/3. So if we plug that in, L is equal 0.738 times E prime, we said came out to 1.5 million, I believe, 1,500,000 PSI. And let me just put a bracket right here, and that's going to be multiplied by I 0.202, 0.202, and then close the bracket and divide the whole thing by W. Now wait a minute, W, we're not using this one because it's total vertical. We're using load for deflection, which is 108 pounds per square foot, or which said 108 pounds per square foot is the same as divide that by 12. Divide that by 12. Divide by 12 should come out to, what do I have? 9 pounds. Load is going to be 108 pounds per square foot, which we're going to multiply by 1 foot strip, and it's going to be converted to inch, become a 9 pound per inch. And this thing is going to be by power of 1/3, and my allowable span for deflection based on L over 360 comes out to 23.8 inches. Keep this number in mind. And for bending was 23.3 inches. So they're pretty close. Now we're going to go ahead, because the code says either go L over 360 or go 1/16. So we could do the same thing. What if it's delta max equal 1/16 of an inch? And we're going to set that equal to the same equation over there. WL by power 4 divided by 145 EI. Let me change color here. Pink is good. So we go ahead and use that. Based on that, we can go ahead and say, okay, the L is going to come out to be allowable span length. It's given by this equation, 1.375, 1.735 by E prime I, divide that by W by power 1/4. And plug that in. L is equal 1.735 times E came out 1,500,000 PSI, and moment inertia came out to be 0.202, and divide that by the weight, which we said it was for deflection is 9 pounds per inch, and by power of 1/4, and that should come out to 23.5 inch. Now, again, the whole idea is we're going to go ahead, we select the sheathing right here, so we check for bending, then we check it for deflection, then we're going to check it for shear, and just like a beam, we check all 4 criteria: bending, shear, bearing, and all that stuff. So let me go ahead and erase this section, and then we continue. Maybe I can, actually I'm going to go ahead and do it right here, see if I can fit it right here. So let's check for rolling be LE F prime RS rolling shear time IB divided by Q, which we already have that from the table, and divide that by 0.6 W. So that's going to come out to, that was 82, which you get from the table. PSI time IB came 0.2, no, I lied. IBQ came out to be 618. And divide that by 0.6 time W. Now W we're going to use is not for deflection, is a total load 158 time 1 became, I erased it I think, 158 pound per foot, which we said it came out to be 13.16 pound per inch. So this will give us 64.2 inch. Oh, this is not controlling, obviously. Okay, so for a 3-span, we did all the check. We got 64. For deflection, we got 23.8. We had 23.5. That's another one. And the next one we had, it was for bending, which was 23.3 inches. So which one control? Right here, 23.3 inch will control. And let me just use a different color here for good luck. I'm going to say, okay, this right here, control. And because the plywood is an 8-feet sheet, and we're going to have a 5-span, supported span to fit into 23 inches. So let's make an equal span. I'm going to say, okay, 8 feet, let's make that to an inch. So that's 96 inches divided by 5. And that will give me 19.2 inch equal span. So I'm going to come in here, I'm going to say, okay, we're going to use this as a 19.2 inch. And that's our number. Let me clear this up, and then we're going to go ahead, continue. We designed this, then we're going to design either this one, yeah, this one or that one. Let me erase this. It's a lot of work. So ready? 1, 2, oh yeah, now we business. So the problem says to us this stringer is every 5 feet. So if I get the stringer, it's every 5 feet. And let's bring the stringer down here. We got the stringer right here. I don't know what the size of it is. That's the ST for the stringer. And they are every 5 feet. So if I get a, whatever number I have, if I get a 10-footer, that means I'm going to have to be a 3-span. It's going to go across, 3-span, and this will be the joist if you look at it from the other angle. Okay? And so it's going to go multiple 3-span. We're going to go ahead and design this, and we're going to use in Douglas fill large. If you look on the table right here, what we have, we're going to use NDS. Let's look at the NDS table 4.3.1, and that will tell us. So if you look at those of you who took timber design with me, if you go back to NDS table 4.31, when we calculate a bending stress for a timber, the capacity of the bending stress FAB based on a species of the material is given to us. In this case, it's Douglas fir large, which comes out to 1,000. Per table, you can see it's 1,000 psi. However, in timber design, to calculate the bending stress, you have to multiply by these factors, and these factors all depend on the environmental condition, the time limit, and all that stuff. So you go ahead and read on that, and CD is for how long you have it, and CM, CT, CL, CF, CFU. Depend on the size factor. Is it going to be inside? Is it going to be outside? What's the temperature is going to be? Is it going to be pressure treated? And all that stuff. Is it going to be repeated every so often? And these most of these time, a lot of time you find out these going to be equal to 1, except for CD1. In this case, they all equal 1. CD is equal 1.5. So our F prime B is equal 1,000 times 1.15, and that gives us 1,150 psi. So now going back to NDS table 4A or ACI formwork 4.3, the shear stress is going to be 180 psi. Margin of elasticity is going to be 1,500,000 psi. Okay, so we're going to go ahead and do load calculation. Our total load was 158 for a strength pound per square foot. Let's convert this to an inch. Because it's a square foot, it'll be 12 times 12 is 144. And then we're going to multiply by the turbotree width, okay? And the turbotree width for the beam spacing is 19.2 inch. Remember, take a look at this beam, which is going this way. And you want to know, and this beam has that much concrete on top of it. And so now you want to find out what is the portion pound per foot. So we're going to multiply by a turbo 3, which is 19.2 inches, and that's going to come out to 21.2 pound per inch, or same as 253 pound per foot. And for deflection, that's for strength. For deflection, we're going to take out the life load, and which is going to be 108. So we're going to say, all right, 108 divided by 144, just like above, and multiply by 19.2, and that will give me 14.4 pound per inch, or same as 173 pound per foot. Okay. Now we have these, and now we got to go ahead and do check for bending. So let's say, okay, check for bending. The equation we have F prime B times section modules comes out to be, for 3-span, WL divided by 10. That's a W squared divided by 10. And now we're going to go ahead and we say, all right, what is the section module comes out for 3-span? It's going to be WL squared divided by 10 F prime B. Okay, now we have that. We can go ahead and calculate it. Let me see if I can fit it in there. It's going to be 21. I'm not going to have a room. 21.2 times, the length is a 5 feet spacing, so that's going to be 60 inches. So the 60 by power 2, divide that by 10, and we said F prime B came out to be 1150. 1150. Do I have a room? I do. And then that's come out to 6.6. So our S has come out to 6.6 inch by power cube. Keep that number in mind. Then now we're going to go ahead and check for deflection. Check for deflection. And we're going to say, okay, for L over 360, so I'm not going to explain that. I explained it last time. Delta is going to come out to be WL by power 4 divided by 145 E prime I. Or we're going to go ahead and modify this. We're looking for I because we know all of them except I. I is going to come out from here. 360 WL by power 3, divide that by 145 E prime. So my I is going to come out to be 360 times W, which was for deflection. W is 14.4 pound. 14.4 pound per inch, and time 60, that's the length, divide that by power 2, divide that by 145, and the E prime was 1,500,000 psi. So it comes out 515 inch by power 4. Now we're going to go to India's table, 1B, have it on the screen right there. And we're going to find out which, there's a 2x4 fit here or 2x6. 2x4 is going to fail because the section module is too big. So let's going to use, say, if we pick 2x6, we have these qualities. And in 2x6, we have S is equal 7.56, which is bigger than 6.6. We OK here. And let's check the moment inertia. I is equal for 2x6, I is equal 20.08, which is bigger than 5. That's way okay. All right. But if I use 2x4, 2x4 will not make it because the section doesn't make it. So this is for bending. Let's go ahead and check for shear. I'm going to erase right here. I'm going to check for shear now, and shear is given for 3-span is given by this equation, and then we're going to look out for BD, solve for BD because we have all of them. So BD is going to come out to be 0.9, and W for shear is going to be 21.2 pound per inch. Time LL is 60 inches. Divided by F prime V, I just erased it, and that was 180 pound PSI. And we're going to get 6.33 inch square, and the area for 2x6, which is per book, and so 2x6 area is basically same as 1.5 inches by 5.5, and that comes out to be 8.25. So this number is less than 8.25. Our board is bigger than 6.33, then we said okay. It passed bending, it passed shear, and it passed deflection. Therefore, this right here, it's going to be a 2x6, and the spacing order is given. It's going to be 60 inch apart, looking at the other way. The span underneath it is going to be 60 inch. I erased it down here. We're going to move on to the next step, which is step 4, stringer size and spacing. The size has already been given to us at 5 feet apart. So let's go ahead and check the load for bending. We said the load was 158 pound per square foot. And if you multiply that by turbometry width of 5 feet, and that comes out to 790 pound per foot, or same as 65.8 pound per inch. Then load for deflection, it's going to be same thing, no, not 150, I take it back, I lied, 108. I put it out there so I can remind myself. 108 pound per square foot times 5 feet, and that comes out to 540 pound per foot, which is the same as 45 pound per inch. Okay. So we're going to go ahead and check for bending. For 3-span, S is a section modulus given by WL square. Divide that by 10 times F prime B, just like last problem. W comes out here 65.8 multiplied by 60 inch square, which is 5 feet, and divide that by 10 times, and F prime, which I had erased, was 1,000 here. And for this particular wood that we're going to use, the other one was different. So that's going to become 23.7 inch by power 3. Let's go ahead and check for deflection now. And for deflection, we're going to go ahead and for L over 360. Okay, moment inertia is equal 360 WL by power 3, divide that by 145 E prime. So I got 360 times deflection came out 45 pound, remember? 45 pound per inch, and times 60 by power 3, divide that by 145 times 1,500,000, and I comes out to be 16.1 inch by power 4. Next thing we're going to do, no, I got a different color. Next color will be blue. Okay, check for, we did bending, we did shear, we did deflection, no, shear, and equation from before, BD is equal 0.9 WL, divide that by F prime V, which is 0.9. W is total load, which is a 65.8, and L is a 60 inches, divide that by 180. And BD comes out to be 19.74 inch square. So now, here you're the designer. You're going to design this wood. Remember, in a temporary structure, don't be afraid to over-design it, because you after you design something like this, excuse me, after you design something like that, you have no control over what the contractor, what the worker, when they install this, what they're doing. You always heard that the building fails because the worker did something they're not supposed to do. So again, don't be afraid. Over-design it. So what we're going to use, as number, you can use 3 by 10. You look at the table 1B. From table 1B, select whatever you want. I'm going to just say I'm going to use 4 by 8. That's a nice piece of strong wood, is commonly available. And if you use 4 by 8, then you have your S is going to come out for 4 by 8. Section module is about 30.66, which is bigger than 23. So there's okay there. And then your moment inertia is going to be 11111, which is bigger than 16.1, way bigger than 16.1. So you pass the flying color there. And the area of this, it's going to be 25.38, which is bigger than a BD of 19.74. And we okay. So this is a good design. When we design these things, so we design everything. We designed for the plywood, we did that. We designed for the stringer, we did that. We designed for the, for the joist, and with the stringer, we just did that. One more left, and that is the bearing. What is the bearing of this joist on top of this stringer, and what is the bearing of this stringer on top of this piece of plate that is on top of the column, or it could be a steel column, whatever, that supports that. So let's do that. I'm going to go ahead and erase this right here. Okay, so we're going to go ahead and do this bearing stress between those. The stringer is going to be like this right here. This is my stringer. And the stringer, as I said, came out to be 4 by 8, right? This came out to be 4 by 8, so that means a 3.5 by 7.5. So this is going to be 3.5 inches right here. Okay. And then we're going to have this one is a 2 by 6. So the 2 by 6 is going to be resting on here. And this is a 4 by 8, which came out to be 3.5. This is a 2 by 6. And it's this, I mean, this is 1.5 inches, 1.5 inches. So this is the area of bearing. So the area is 1.5 inches by 3.5. Keep that in mind. First, we're going to calculate the load. Calculate bearing between the stringer and joist. My load first is going to be, we said the distance is 19.2 inches. Multiply that by, divide that by 12, and then we're going to multiply by 60 divided by 12. Okay, so that gives us a total area, and we have 158 pound per square foot. So the total load is going to come out to be 1,264 pound. Then the stress perpendicular to the grain is going to become 1,264 divided by this area, which is 1.5 inches times 3.5, and that will give me 241. But what is the capacity of bearing of the stress? The capacity is going to be, let's calculate the capacity. The capacity here is going to be F prime perpendicular to the grain. It is F, the compression stress perpendicular to the grain, times the adjustment factor, which was the all bunch of ones, CM, CD, and C1 and CB. Compression perpendicular to the grain time all this adjustment factor, which these all equal 1 anyway. It comes out to 625 from NDS 4A or ACI, which you see on the table right there. This number is less than 625, so we okay. Continue with that. We're going to go ahead and calculate the stress between the joist and the column here. I'm going to go ahead and calculate this here. First, we're going to find this reaction, which is given by this equation. It's up on the screen. RB is equal RC is equal 1.1 times WL. That's a W, which is 1.1. Our W was 158. So the reaction for here, based on the spans given, 3 spans, max would be 1.1 times WL. So that's 1.1. Our W we calculated was 790 pound per foot, and multiplied that by L, which was 5 feet. That comes out to 4,350 pound. The area that is going to occupy, let's go ahead and just draw this again. This is a 4 by 8. So this is a 3.5 inch. And this area that is given is a steel bracket, and they said it's about 11 inches. It's 11 and a half inch. So now the area is going to be 11.5 by 3.5. So we already have the capacity, so we're going to calculate the compression stress due to the load, which is going to be 4350 divided by 11.5 times 3.5, and that comes out to 108 psi, which is less than 625, and we okay. This is basically was a long problem, but that's how you do it. You got to go through all these steps, make sure everything is okay. I hope this was useful. If it was useful, I love your comment, and give me a thumbs up.